Hello and welcome back. We're getting closer to the end of our 24-hour conference, and we have a special presentation for you right now with GSS Inc. Please welcome Alvaro Gil and Othmane Dai. Apologies. Thank you.
Thanks, Max. Hello, everyone. I'm Alvaro Gil, and with me, Othmane Dai. We are from GSS. And we're going to talk about one of our favorite topics today, which is digital twin and collaborative design, how those two topics were combined at the Montreal International Airport to create a smart baggage handling system. We're part of GSS, the Predictive Technologies Division. A little bit about GSS. We're a Canadian-based consultancy firm. We're based mainly in the province of Quebec, but we work with different projects across Canada and the United States. We're mainly focusing in three sectors of activities, which is airports, aerospace, health and life science, and supply chain. We're basically structured in two departments. One of them is the predictive technologies, and the other one is the collaborative design department. And we have different consultants working in the company in those departments with different skills ranging from simulation, data analytics, optimization, AI, Lean Six Sigma, and many others. We work very close with our customers. We try to implement always a close collaboration with them in order to develop sustainable solutions. Among the list of customers, we have different companies ranging from pharmaceutical companies, government agencies, airports, airlines, manufacturing companies, telecommunications, etc. One of our customers that we've been doing business with for a while is the Montreal International Airport. Montreal International Airport is one of the most important airports in North America. They have more than 140 different destinations. Most of those destinations are international destinations, and they have an interesting proportion of passengers in traffic, which is a nice to have metric, a very interesting metric for airports. In 2019, they overpassed the goal of 20 million passengers in terms of flow. And they, during the year 2014-2019, they have a very interesting growth, around 38% in terms of passenger flow. 2020 was a very special year for all airports around the world because of the pandemic. So right now, the traffic in terms of passenger flow is ramping up again. And we're all optimistic that in the short future, we're going to start having a growth rate as it was before the pandemic. So this project is basically part of the preparation for the future growth. So how are we structuring this presentation? Is first of all, we're going to talk about BHS, the baggage handling system. What's the business challenge and the complexity around it? And we're going to explain the HLC concept, which is a way how we approach this challenge. And of course, we're going to talk about the simulation model that we developed for this. Now, I'll let you with Othmane.
Okay. Thank you, Alvaro, and hello, everyone. So we will start by describing the baggage handling system. So basically, a BHS is a combination of conveyor, screening equipments like X-ray machines, automation components, and stations that have a mission to transport and process bags from different entry points to a centralized explosive detection systems, and then distributed toward multiple destination piers. The BHS is a closed, complex system with thousands of interconnected elements. So the complexity basically is due to we have empty trays and loaded trays circulating into conveyors, and also we have bags that are circulating on a belt conveyors that needs to be synchronized in order to load bags on a trays and also to drop bags from the trays. The other complexity of the system is that we have multiple entry points and also multiple exit points. The BHS is also characterized with a high throughput capacity and lots of variability. This variability may come from inside the system, for example, the process time of a bag in a station, and also from outside the system, for example, the input flow of the bags to the system. Like I said in the previous slide, we modeled a BHS with more than 1,000 conveyor and with more than 100 decision points, so resulting in more than 2.8 million decisions daily. So the process starts at the airline counters where the bags are dropped in a conveyors network. So the bags are loaded into an empty trays through a trays conveyor. The loaded trays are going through the explosive detection system, and then the bags are dropped into a conveyors network, and the empty trays are stored into a temporary parking area. The bags that are dropped here join spires and carousels, then transported to the airlines through unit load devices. There is three main types of decisions that a tray should take. The first one is a start and stop decisions. For example, the empty tray should stop at the end of the parking area waiting for the bag, and also the bags should wait at the end of the conveyor waiting for the empty tray. The second type of decision is point of divergence. So for example, a tray should take this segment or the other segment. For example, here we can see that the first bag here went through the first city machine, and the second bag went through the second city machine. And the third type of decisions are the dropping bags. So if we can see here that if the loaded bag have all the necessary authorization to leave the BTS, and also the conveyor lead to the desired destination, so the bag can be dropped onto the conveyor network. Otherwise, the loaded tray don't stop at the decision point. Also, we have many decision variables that we take to control the decisions. The first one is the number of trays in a segment. For example, the number of empty trays in a parking area. Also, we have the number of bags in a system. So for example, the number of bags that's coming for a specific airline counter. We have also the status of a segment. For example, if we took the segment, so the status should be available, out of order, or in dieback. The dieback is a dynamic accumulation of empty trays resulting to a conveyor stopping. If we took an example like a train with trays, so if the first tray stop at the stations, all the remaining trays will stop also. And for the we have also a decision variable that is the status of the tray. So the tray may be empty or loaded. We have also the destination of the bag. So the bag should join which fire. And also we have the X-ray status. So does the bag have all the necessary authorizations to leave the BTS? Regarding the business challenge, we know from the operational reality that flight departures are concentrated in a specific period of the day. For example, we can see here a baggage input flow, and we can see that there is two peaks in the day, one in the morning and the other one in the end of the day. So the design has to support the peak time without affecting the customer service level, and also it should take into consideration random operation events. So given space constraints between trays, the implementation of the bag tray system was successful from a mechanical point of view. But the flow management system presented many improvement opportunities. So the main business challenges that we face are the flights are delayed, so the peak time may change in the day. So also the resource allocation should be adapted. The other main business challenge is that the customer experience is affected at counters and also at the transit drop-off belts if we can no longer push bags into the system. And the other one is the practical capacity that is mainly related to the screening and handling equipment is not used at its full potential. So there is a need for a robust and dynamic system architecture to support the implementation of a smart control automation approach. So that's why we introduced a high-level control approach. And to test the operational improvements in infrastructure evolution, that's why we integrate the digital twin with the high-level control. There is also a need for a strong partnership between key community stakeholders like security agencies, airport authority, VHS operator, airline, and engineering companies to accurately represent the system operations. So that's why we added the second part of our project, that is the collaborative design. To understand the HLC concept, we need to understand the existing control approach. So traditional BHS basically uses local variables that manage the decisions. So we use mainly information of the physical components that are surrounding the decision points. Whether a high-level control uses a system thinking to take proactive and dynamic decisions based on multiple conditions. Let's take an example. If we want to go from point A to point C, we need to take a decision at point B whether taking the blue segments or the green segments. The local approach only considers the status of the green and the blue lines, whereas the high-level control approach considers the upstream demand and also the equipment availability downstream. So the tray might change its destination based on new demand informations, changes in the availability of trays in a parking area, and also it takes into consideration degraded modes. With this change of paradigm, we need to test thousands of what-if scenarios to design a robust logic, and also to integrate lean and agile principle in the design process to simplify the logic. So multiple scenario analysis combined with multi-criterion optimization algorithms leads us to a consolidated set of rules. For example, here we have an example of a high-level control rule. So we want to take a decision at the point P1 that corresponds to the conveyor T29-115A. So we need to choose between continuing to sector 1 or diverting to go to buffer number to sector number 2. So from a human read, the logic is, for example, here. So if we have the buffer 1 and buffer 2 below 5, so the buffer 1 is the number of trays that are accumulated in this line, and buffer 2 the number of trays that are accumulated in this line. It's below 5, then we choose to go through the sector number 1. The other condition, if we have the utilization of a component that is downstream the sector number 1, so if it's below 50%, then we go through the sector number 1. And the third condition, if we have a ratio between buffer 1 and buffer 2 and buffer 3 below 50%, then we'll have to go through the sector 1. Otherwise, we have to choose to go to the sector number 2. This rule is then transformed into a system rule. So in our simulator, we have the ID of the components, the condition, and the expressions that we use within the condition. So this rule is then transformed to a SCADA read to be implemented in a programmable logic controller. This way, the simulation decision platform helps within the design and test of high-level control groups.
Thanks, Osman. So, as you can see, this is a this is a very complex challenge that requires a high-level approach as well as a systemic view. We like this quote, or we bring it a lot into our projects from Herbert Simon, which says that modeling is a principle and perhaps the primary tool for studying the behavior of large and complex systems. We know that this is a very complex system, and we know that modeling and simulation is a key and fundamental tool to explore the solution, the HLC concept in this case. So how does our simulation model look like? First, why do we choose AnyLogic? First, we knew it was a complex system that requires a dynamic architecture and a very flexible software. And we also knew that there were, as Otman said, millions of decisions taken that has to be taken during a runtime simulation. So those simulations needs to be managed by agent-based approach. So combining flexibility, a flexible, a robust system, and an agent-based approach, we knew that AnyLogic was the proper choice for us. Now, other than that, we knew that also there were a couple of very important libraries, which were the process modeling and the material handling. So we use components from those libraries, but we also knew that in order to represent the operational reality, we had to design our own components. So we had to we had to go to the field and capture the real behavior, and then talk to the operator to understand what was the mechanical and electrical behavior, and translate those behaviors into elements that were in the software. So that's why we created our own library, the GSS VHS library, which has our own components that behaves exactly as the VHS elements, including sorters, diverters, discharge, etc. We have a few extra non-tangible elements like the counters on the VHS calculations, which are used for all the buffer calculations and utilization. But I will say that part of the most important elements are the VHS calculations. We take the human reads that Otman described previously and convert that into vectors of Boolean variables, so it can be used and transformed into decision during the simulation. Of course, the integration with external data sources as TXT files, CSV, Excel, and databases was a very important element as well. From the architecture point of view, we have different streams of the data source. Of course, the most important are the rules, including the behavior of each of the components, the decision points. But there is also the flight plan. The flight plan is basically the schedule. How is the schedule going to look like in the future? So what's the destination? What's the airline? What's the flight? And then we have other models that using historical information, they translate this information considering the destination, the type of airplane, airline, etc., and translate that into the input of the bags into the system. So now we have the arrival profile of bags. Now we need the peer allocation to understand how the destination, or where the bags are going to once they are released from the system, which will change. Any peer allocation changes will change the flow going to the sorters. And then the desk allocation, which is basically where are the bags inserted to the system. So all that information is sent to a central database. The simulation platform is also attached to that database. Any combination of HLC rules or changes in flight plans becomes a new scenario. So we have a scenario manager in between that reads all the possible combinations, and of course it performs all the necessary replications in order to achieve a confidence interval. And once those simulations are run, they are sent back to the central database, where we have our own dashboards that help us to read and understand what the results are and compare scenarios. lots of benefits from this architecture and this tool. Of course, we can integrate with operations, which is a primary tool. It's a planning support tool, as for instance, the changing in the flight schedule. Automatically, we require a new simulation to see if this new plan match with the capacity, and of course, how is that going to impact the metrics or the KPIs attached to the customer satisfaction. It's a rapid assessment of operational improvement and system logic. Any improvement in terms of logic, any change of buffer size or even speeds, it can be tested by the simulation, and it will bring back results to let us know if we are on the right track or not. For the infrastructure evolution is also a very good tool. It helps us to test new lines, new equipment, and to know if we are on the right track or not. And we keep a continuous protection of customers' operations. From the technical point of view, we have a modular architecture and ability to isolate subsystems from the simulation, so we can just test a specific loop and know if we are, if for that specific loop mechanically we are correct or not. And it's easy to integrate with the VHS system language. In terms of phases, we've come from different phases of integration. First was the VHS library, then the implementation, the calibration, and all these scenarios that we run from. And now we are in the infrastructure validation and also the one-way phase, which means that we are able to read information from the operations and send back information related with the rules. Our current pipelines in terms of development is the digital twin, which is having the two-way fluid communication between the simulator and the VHS system. So let's take a look at the model. I lost my, oh, there you go.
So this is the main page of the simulator, where we can change the system parameters, the input files, and also the saving informations. Here we can see the global view of the system. It's a closed tray system with multiple entry points. So the trays go to a centralized explosive detection system before joining the exit points. There is also multiple parking areas where we can store the empty trays where the demand is lower. Here we can see the introduction of bags into the system. So the synchronization between bags and trays to load bags on the trays. Here we can see the movement of merging two lines into a main line with the respect of the distance constraints between trays, and also the priority that is set up on the simulation main page. Here we can see the movement of stacking empty trays one above the other and forming a batch of 4 columns to maximize the utilization of the parking area.
As you can see, all those elements had to be manually created by us to represent the reality, as well as this, for instance, is the exit of the system. So this is the communication with the sorters. Basically, these are the discharge once a tray arrives to a decision point. This is one of the decisions that Odman was describing at the beginning. They have to decide based on the status of the bag if they drop or not. This is just a general 3D overview of different components working. As you can see, there are several levels. So sometimes from the 2D, it looks like a single line, but we have different lines interacting above and beyond. Once the results are available, once the simulation is done, we have this web interface where we access internally to analyze the results, compare all the scenarios, and we'll calibrate the model and send information back to the customer. This is in general terms how the simulation looked like. I just to quote one screen. Yeah, thank you. Thank you. For some reason, I'm starting one last slide. There you go. So in terms of results, sorry about that. In terms of results, we know that thanks to this development and this long-term collaboration with all the stakeholders, we were able to reach the target practical capacity that we established at the beginning of the project. We know that the airport is ready to handle the recovery phase, and we were able to prove the high-level control strategy, as well as having and developing a stable platform and mature platform simulation for the airport. We know that we have a rapid decision making supporting tool for operations and planning. And then we have we are able to easily identify bottlenecks, issues, as well as support the infrastructure growth decision. It's a very good tool for contingency plan, and it has demonstrated efficiency gains. So now in the pipeline, it's finishing we have to finish this digital twin, which is the next phase. And I think that's it. Our time is over. Thank you very much. We have a question here. Says a very interesting application. Are you planning to connect this digital twin with passenger process and simulation model? Sure. It's part of the future projects. So far, we are connecting the simulation with the peer allocation as well as the counter passenger allocation. So we are able to connect part of the passenger process, but of course, part of a future project is to extend this to get to the passenger terminal as well. We have another question. It says, how long does it take to simulate an hour of real time? Well, I will say a full day of simulation with the heaviest flow. It has two ways to see it. If we simulate it with the 3D and 2D animation, it may take 30 to 40 minutes, a full day. But if we do this headless, just in a custom experiment, it may take 4 minutes around. It looks like you have a very large number of agents performing complex calculations. Did you encounter computational performance issues? It's very demanding in terms of the number of computation and calculations during the day. That's why we had to do lots of interactions, and we also had a big support from the AnyLogic support team, trying to optimize each one of the behavior of our components. As the minor change in terms of an extra calculation, it will represent lots of extra time in terms of calculation and simulation performance. So yes, we had to be very optimized in the way how we design the elements. Well, I think that's it.
Thank you once again for a very exciting presentation. Very, very impressive. We are almost done with our 24-hour live conference. So we will be having one of our last presenters up next. Just 2 more. See you soon.